Hello, dear students. For the second grade exam, I chose 30 questions, and here in this video I will try to explain them. First question 2. What is the difference between the internal energy of the gas sample and the internal energy of a solid object? So let me write it here. Here we are talking about ideal gas. And also we have a solid object. So internal energy of ideal gas is only depends from in kinetic energy. But for solid objects, internal energy is the sum of kinetic energy, like of molecules, and plus potential energy of the molecules. What does potential energy means? Molecules in solids and liquids have intermolecular connections. That's why they have potential energies. So also that means we also need to take into account that energy. Question 3. Why can't we change the internal energy of a gas sample without changing its temperature? Because in ideal gases, the internal energy depends from only kinetic energy, and there are no other energies, like, for example, potential energy. So that means if the internal energy increases, it results in only increase in kinetic energy. So kinetic energy is an indicator of increasing of the speed of each molecule. So the speed is an indicator of increasing temperature. So there are no other energies except kinetic energy. That's why in ideal gases it works only in this way. Question 5. Both heat and work are means of transferring energy to a system. What is the difference between them? So here we're talking about heat and work. So heat is a thermal energy, but work is mechanical energy. So for thermal energy, we know that thermal energy can be transferred in 3 ways, like conduction, convection, and radiation. But mechanical energy can be transferred by applying a force. It transfers under force or under pressure. So that is the difference. Question 6. Does the energy of the system increase or decrease when it does work on the surroundings? So here, let's draw a system. Here, surrounding, and here is the system. So it says when the system does a work on a surrounding, that means system is expanding to the surrounding. That means it is using its own energy to do some work. That means the system is gonna lose some amount of energy. Question 8. What is the relationship between work done by a system and work done on a system? So here we should consider a cylinder piston system. Here there is a movable piston, and let's say there is a gas inside, like ideal gas, let's say. So we transfer a heat to the system. So what happens? These molecules start to move faster, and it results in high pressure, in pressure increase. So that means the gas starts to push upwards the piston, right? But by the third law of motion, for every force, there is an opposite reaction force of same amount, of same value. So it's called reaction force, and it has negative sign, like negative F, let's say. So if there is so here, this piston, for example, moves up for a height of h, let's say. So work done by a system will be equal to F times h, yeah. But also the surrounding work done on a system will be equal to negative F times h. So as you can see, they have the same value but with the opposite sign. So we can make the final equation, final definition, or it says work done by the system will be always equal to negative work done on the system. Question 11. A gas sample does 320 joules of work as it absorbs 700 joules heat from the surrounding. What is the internal energy change of the gas? So here we need to apply the first law of thermodynamics, which states that heat given to the system can be spent in two ways: to increase the internal energy of the system and to do a work by a system. So here, firstly, let's write the given. It says a gas sample does 320 joules of work. That means work done by a system is equal to 320 joules of work. And then it absorbs 700. That means Q is positive 700 joules. So the last step, we just put all these numbers to the equation. So 700 joules is equal to delta U plus 320 joules. So delta U is going to be the difference of them. So delta U will be equal to 380 joules of change in internal energy. Question 12. The internal energy of a gas sample increases by 280 joules when it does 185 joules of work. What amount of heat is absorbed by a gas? So here it is better if we write the given firstly. The internal energy of a gas increases, yeah? So we write delta U will be equal to positive 280 joules. And then we have the system does a work, so work done by a system is positive 185 joules. And we need to get the heat absorbed by the system, yeah? Here we have to apply first law of thermodynamics, which states heat given to the system can be spent to increase the internal energy of the gas and to do a mechanical work. So here Q will be equal to 280 plus 185 joules in joules, yeah? So Q will be equal to 465 joules of energy transferred to the system. Question 14. The internal energy of a gas of a system increased by 100 joules when it absorbs 400 calories of heat. What is the work done by a system on the surroundings? So let's write the given firstly. Delta U change in internal energy is positive 100 joules. Then it absorbs 400 calories. So Q is equal to 400 calories, but we need to convert it into joules. So we know that 1 calorie is equal to 4.18 joules. That means I multiply 400 by 4.18, so it's equal to 1672 joules of work. And then to get the answer, to get work done, we need to apply the first law of thermodynamics, which states Q is equal to delta U plus work done by a system. So here work done by a system will be equal to the difference of Q and delta U. So work done by a system is equal to Q is 1672 joules minus 100 joules. So it's equal to 1572 joules of mechanical work. Question 17. A gas expands slowly against a constant pressure of 200 kilopascals, doing 100 joules of work during the expansion. What is the volume change of the gas? So given is pressure, which is 200 kilopascals, and work done by gas, which is 100 joules. And we need to find what the value of delta V, change in volume. Here we just use only one formula. We just use one formula, which is work is equal to P times delta V. So delta V is equal to work over pressure. So here in this question, delta V will be equal to 100 joules over 200 times 10 to the power of 3. So delta V will be equal to 0.5 times 10 to the power of negative 3 meters cubed, or I can show it in liters. It will be 0.5 liters. Question 19. A gas expands as shown in a figure in a PV graph. What is the work done by the gas during the expansion? So here we need to know that area under the line gives the work done by a gas. So here, as you can see, by defining the area, we can separate it into two parts. We have this rectangle, area 1, let's say, and we have area 2, so this one. So the area gives the work done. Let's solve it. So work done biogas because it is expanding will be equal to the area, which is 15 minus 6. Just hold on, let me write it here. So work done by a system will be equal to 15 minus 6. I multiply it by 10 to the power of negative 3 to convert liters into meters cubed. And then I multiply the next side, which is just 1, but I multiply it by 10 to the power of 5 because the pressure is given in atms. That's why I multiply by 5. And plus the second area, which is 15 minus 6 times 10 to the power of negative 3 times 2 minus 1 times 10 to the power of 5, but divided by 2 because this is the triangle. So work done by a system will be equal to 9 times 10 to the power of 2 plus 4.5 times 10 to the power of 2. So it is equal to 900 plus 450, which is equal to 1350 joules of work done. Question 22. Internal energy of a gas increases by 150 joules as it absorbs 250 joules of heat under 100 kilopascals of constant pressure. What is the change in volume in centimeters cubed? So here, let's write the given here firstly. We have delta U, which is positive 150 joules, and then Q, which is 250 joules, also positive, and pressure, which is constant at 100 kilopascals, and we need to find delta V, change in volume in centimeters. So to solve this question, we need to apply the first law of thermodynamics again. So Q is equal to delta U plus work done by the system. So here I can replace I can replace W with delta U plus P times delta V. So if I rearrange it for delta V, it will be equal to Q minus delta U over the pressure. So let's just put the numbers. Delta V will be equal to 250 joules minus 150 joules over 100 times 10 to the power of 3. So it is equal to 100 over 100 times 10 to the power of negative 3, which is equal to 10 to the power of negative 3 meters cubed. So delta V is equal to 10 to the power of negative 3 meters cubed, or I can convert it into centimeters cubed by multiplying it by 10 to the power of 2, which is cubed. So it will be equal to 10 to the power of 3, or just 1000 centimeters cubed. Question 23. So it says the temperature of 56 grams of nitrogen gas increases from 20 to 200 Celsius as it absorbs heat at constant pressure. The internal energy of a gas increases by some amount of energy during the process. What is the amount of heat absorbed by a gas? So, and also molar mass is given. I already wrote all the givens, and now let's just make the solution. Here we need to apply the first law of thermodynamics, which is Q equal to delta U plus work done by the system. So here Q delta U is given. I can replace work done by the system by pressure times delta V, because it says pressure is constant. That's why. And now, but the volume delta V is not given, but instead of it, change in temperature is given. We can also apply, that's why we can apply the ideal gas equation, which is PV nRT. That means we have to make two equations for two states of the gas. It will be pressure volume initial is equal to nRT initial. And the second one is PV final is equal to nRT final. So if I subtract these two equations, like PV final minus V initial in the brackets will be equal to nR T final minus T initial. So shortly, P delta V is equal to nR delta T. So that means here now, instead of P delta V here, I can put nR delta T. So our equation will be changed to this one. Q is equal to delta U plus nR delta T. And now let's just solve it here. Q is equal to 7,480 joules plus number of moles can be shown as the division of the mass to molar mass. Yeah, we know that mole is equal to mass over molar mass. That means 56 grams over 28, and multiplied by R constant is 8.31 times the difference in the temperature is 180. Here it's not necessary to convert it into kelvins because we only need the delta T. That's why, because we're gonna get the same number for Kelvin and Celsius in delta T. That's why. So the answer should be 80 joules plus 991.6, which is equal to 10,471.6 joules of energy was absorbed by a system. 24th question. The figure shows PET graph, pressure temperature graph for an ideal gas. What is the internal energy change of the gas between states as it absorbs 1800 joules of heat during the process? So one thing that you need to know, that the extension of this line, as you can see, it intersects the origin point, intersects the initial point, the coordinate, so the graph, yeah. So that means in a PT graph, this means it is an isovolumetric process. Isovolumetric, as we know, means volume stays constant. So what does this mean? Volume constant means there is no change in volume, so delta V will be 0. So if there is no change in volume, that means there is no work done in a system, so work done will be equal to 0. And that means the first law of thermodynamics, which is Q equal to delta U plus work by, will be simplified to Q equal to delta U. So, and also here it says it absorbs 1800 joules of heat. That means Q is equal to 1800 joules, which is also equal to change in internal energy. So it is positive 1800 joules of internal energy change. Question 28. The temperature of 2 moles of ideal gas increased from 20 to 120 Celsius as it absorbs 5,870 joules of heat at constant pressure. What is the change in internal energy of the gas? So here we apply first a law of thermodynamics, which is Q equal to delta U plus work done by the system, and it means delta U will be equal to Q minus work done by the system. Here we can, instead of work, I can put P times delta V, but change in volume is not given, but instead change in temperatures are given. Change in temperature is given. So I will replace it with another equation, which is Q minus NR delta T. So that means delta U is equal to 5,870 minus 2 times 8.31 times the difference in temperature is 100. So it should be equal to 4,155 joules of internal energy change. Question 37. Define an adiabatic process. How can we achieve an adiabatic process? Definition is adiabatic process means there is no heat exchange with a surround. things. So we can achieve it by two ways. It can be achieved in two ways. So first one, it must be very fast process, like in an engine. There is no time for heat exchange with the surrounding, or it should be isolated system. By the definition, heat exchange cannot happen. Question 38. 1 mole of a gas sample is compressed to half of its original volume. Is the gas hotter at the end of an adiabatic or isothermal compression? So let's define them firstly. Adiabatic means there is no heat exchange with the surrounding. That means heat Q given or taken out from the system will be 0. That means the first law of thermodynamics will be simplified to this. 0 will be equal to delta U plus work done by the system. That means delta U is equal to work done by the system, or internal energy change will be equal to work done on the system. So this means by doing a positive work on the system, by compressing it, by applying a force, internal energy can be increased. So that means in ideal gas, it results in increase of temperature. But for isothermal process, it says isothermal, that means temperature stays constant. So the answer is the gas gets hotter at the end of adiabatic process. Question 44. 1 mole of an ideal gas expands adiabatically, doing 20 joules of work on the surroundings during the expansion. What is the change in internal energy of the gas if the initial volume is 0.015 meters cubed? So firstly, let's define what is adiabatic process. Adiabatic means there is no heat exchange with the surrounding. So that means first law of thermodynamics will be written in this way. By the system, so that means delta U is equal to negative work done by the system, or delta U will be equal to work done on the system. So, and all it says by doing 20 joules of work on the system. That means work done on the system is positive 20 joules, so which is also equal to change in internal energy. That means by doing 20 joules of work to the system, internal energy increased by 20 joules. Question 45. An ideal gas sample isothermally expands from 0.3 to 0.8 liters. What is the change in the internal energy of the gas during the process if the initial temperature is 300 kelvins? So here in this question we are considering the ideal gas. So that means the internal energy of the gas can be only increased by change of the temperature. At the end it says the temperature stays constant if the temperature stays constant, it means there is no delta T. Delta T is 0. If there is no delta T, it means delta U will be equal to 0. Question 47. A gas sample absorbs 200 joules of heat at constant volume. What is the change in the internal energy of the gas? So here we apply first law of thermodynamics, which is Q is equal to delta U plus work done by the system. And let's put the numbers. A gas sample absorbs, that means Q is equal to 200 joules, is equal to delta U plus, here the work can be written as P times delta V. So in this question it says volume is constant, that means delta V should be equal to must be equal to 0. That means our equation will be simplified to this one, 200 joules just equal to change in internal energy, which is positive. Question 50. What is the change in internal energy of 200 grams of ice as it melts at 0 Celsius? Neglect any volume change. And the constant, the melting constant is given here. So to solve this question, firstly, we have to write first law of thermodynamics, which is this one. And here it says there is no volume change. We just neglect volume change. That means work done by the system, work done on the system, or will be equal to 0. So Q, heat given to the system, will be spent to increase the internal energy. And here it says the ice melts. Melts meaning it needs some amount of energy, some amount of heat to be melted. That means the system or the ice is actually absorbing that energy. So that means, so instead of Q will be positive, and here as it melts we can use this constant melting latent heat of fusion of the ice. So it will be Q is equal to M times LF, which is equal to delta U. So delta U is just equal to 335 times 10 to the power of 3 times 0.2 kilograms. And it is equal to 67 times 10 to the power of 3, or which is equal to 67 kilojoules of change in internal energy. Question 60. A steam power plant burns 50 tons of coal every hour. The useful power output of the plant is 130 megawatts. What is the efficiency of the plant? So it would be better if you write the given. So we have the mass, which is 50 times 10 to the power of 3 kilograms. And then we have time, which is 1 hour, or which is 36,100 seconds. And then we have the power, which is 130 times 10 to the power of 6 watts. And then we have the burning efficiency, burning constant, which is 30 times 10 to the power of 6 joules per kilogram. And now to solve it, we have to use efficiency equation. Efficiency is useful work over total heat given to the system, yeah? So work can be replaced with the product of power times time, and Q can be replaced with mass times the Q of the coal. So the efficiency is equal to power is given, which is 130 times 10 to the power of 6 times the time is 3600 over the mass is 50 times 10 to the power of 3 times Q is 30 times 10 to the power of 6. So if you calculate, you have to get 0.312, or it is 31.2% of efficiency. Question 70. A Carnot engine operates between a hot reservoir at 327 Celsius and cold reservoir at 27 Celsius. How much work does the engine do if it absorbs 800 joules of heat from the hot reservoir? So here we have to use two equations, which are, first one is the efficiency of the Carnot engine, which is 1 minus temperature cold over temperature hot, and efficiency of the engine, which is work over heat given to the system. So that means firstly we have to find the efficiency of this engine. We have temperature cold is 327 Celsius or 600. This is temperature hot kelvins, and we have cold temperature, which is 27 or 300 kelvins. Now let's find the efficiency, which is 1 minus 300 kelvins over 600 kelvins, which is 1 minus 0.5 equal to 0.5. So the efficiency, we found the efficiency. Next step, we put the efficiency to the second equation. So efficiency is equal to work over Q. If I rearrange it for work, it will be work is equal to efficiency times Q. So our work is equal to 0.5 times 800, which is equal to 400 joules of useful work. Question 2. The root mean square speed of molecules of helium gas is 500 meters per second. What is the average kinetic energy of the gas molecules? So for gas molecules, kinetic energy average is equal to mass of one molecule times velocity squared average over 2. Here velocity squared average is not given, but instead root mean square velocity is given. We can substitute it in this way. We know that square root of velocity squared average is actually VRMS. So if I get rid of this root, that means square root, it's gonna be velocity squared average is equal to velocity RMS squared. That means we can change this formula to this m0 times velocity RMS squared over 2. And here molar mass is given, but m0 is not given, but we can define it from another equation. We know that m0 is equal to molar mass over Avogadro's number, and so that's it. So energy kinetic average will be equal to molar mass over Avogadro's number times V RMS squared over 2. So next is equal to, let's put the numbers. Molar mass of helium is, I will write it here. It's 4 grams per mole, but here we need to convert it into kilograms, so it's gonna be 4 times 10 to the power of negative 3 kilograms per mole. And let's put it here, 4 times 10 to the power of negative 3 over Avogadro's number is this number, 6 times 10 to the power of 23. So 6 times 10 to the power of 23 times 500 squared over 2. So if you calculate everything correctly, you should get 8.3 times 10 to the power of negative 22 joules of energy, kinetic energy. Question 3. By what factor must we increase the RMS speed of the gas molecule to increase the average kinetic energy of the gas molecule by factor of 4? So here we have to write kinetic energy formula, which is m0 v RMS squared over 2. Now if I rearrange it for VRMS, it's gonna be VRMS will be equal to energy kinetic over m0 and in a square root. So if we quadruple the kinetic energy, so VRMS nu is gonna be 2 times 4 energy kinetic over m0. So that means if I take out of the root this 4, it's gonna be 2, and in the square root it is 2 energy kinetic over m0. So the only difference of new velocity RMS is of this 2 here. That means we must factor it by 2. Question 7. A sample of nitrogen gas contains 10 to the power of 20 nitrogen molecules in 1 centimeter cubed volume. The root mean square speed of nitrogen molecules is 500 meters per second. What is the pressure of the gas? So I already wrote everything here. Also, the molar mass is 28 grams per mole. Or, I will write it here too. 28 times 10 to the power of negative 3 kilograms per mole. And we have to find the pressure. So pressure is equal to 2 over 3 multiplied by the concentration and kinetic energy, which is 1 over 2 times m0 v RMS squared. Just have to use this formula. Let's just put the numbers. Pressure is equal to 2 over 3. Here, concentration is not given, but we know that concentration is equal to number of molecules over the volume. So number of molecules is 10 to the power of 20 over the volume is in meters cubed is 10 to the power of negative 6 times 1 over 2 times m0. Also, mass of one molecule is not given, but m0 can be found by dividing molar mass to number of Avogadro. So it is 28 times 10 to the power of negative 3 over 6 times 10 to the power of 23 and multiplied by 500 squared. So if you calculate everything, you have to get 388.9 kilopascals of pressure. Question 17. A 0.05 kilogram gas sample is kept at 20 liter container under 100 kilopascals of pressure. What is the RMS root mean square speed of the gas molecules? So here we have to use pressure formula, which is 2 over 3 multiplied by the concentration multiplied by the kinetic energy, which is 1 over 2 m0 v RMS squared. And here also we can write it like this: concentration is equal to number of molecules over volume times 1/2 times m0 and VRMS squared. And here the product of number of molecules and m0 is just a mass, so we can write it like P is equal to, here it is 3, 2/3 mass over volume times 1/2 VRMS squared. So the question is root mean square velocity, so let's rearrange it for root mean square velocity. VRMS will be equal to 3PV over m, and in a square root. So we know the pressure, we know the volume, we know the mass. So 3 times 10 to the power of 5 times volume is 20 times 10 to the power of -3 in meters cubed, over the mass is 5 times 10 to the power of -2. So if you calculate this, you have to get 346.4 meters per second velocity. Question 27. What amount of heat is needed to increase the temperature of 2 moles of monoatomic gas from 20 Celsius to 120 Celsius at constant volume? So here we have to apply the first law of thermodynamics, which is Q is equal to delta U plus work done by the system. But in this question it says volume is constant, that means work done by the system is gonna be 0. So our formula will be Q is equal to delta U. And how do we find heat? So to find heat we need to know change in internal energy, and for it we can use, it says the gas is monoatomic, and we know that internal energy of monoatomic gas is equal to 3/2 nRT. So that means for delta U it's gonna be 3/2 n R and delta T. So Q, given heat to the system, is equal to 3/2 n R delta T. Let's solve it. 3/2 times 2 moles, 2 times 8.31 times delta T is 100. So if you calculate, you have to get 2,493 joules of energy. Question 28. What amount of heat is needed to increase the temperature of 2 moles of monoatomic gas from 20 to 120 Celsius at constant pressure? So here we apply first law of thermodynamics, which is Q given heat to the system can be spent in 2 ways to increase internal energy plus to do a mechanical work. And here so we can replace, here we have to use 2 additional formulas. It says the gas is monoatomic, that means internal energy of monoatomic gas is equal to 3/2 nRT. Also, at constant pressure, the work done is equal to P delta V. And also by applying the ideal gas equation, we will substitute work with nR delta T, because instead of volume change, there is the change in temperature is given. So final formula is Q is equal to 3/2 nRT. Final formula is, one more thing. So from monoatomic gas, we know that delta U of monoatomic gas is gonna be 3/2 N R delta T. So we're gonna substitute these two formulas to the first law of thermodynamics. It's gonna be 3/2 N R delta T plus N R delta T. So Q is equal to N R delta T, and in the brackets 3/2 plus 1, and Q is equal to nRT times 5/2, and this is our final equation. Let's put numbers. There are 2 moles multiplied by 8.31 times change in temperature is 100. So you have to get 4,155 joules of heat. Question 37. During an adiabatic compression, 83.1 joules of work is done on a monoatomic gas sample, which increased the temperature by 10 kelvins. Find the number of moles of the gas. So here, let's write the first law of thermodynamics. Q is equal to delta U plus work done by the system. And it says it is an adiabatic process. That means there is no heat exchange to the surrounding. That means delta U will be equal to negative work done by the system, or delta U will be equal to work done on the system. And so we know that work done on the system is given, which is 83.1 joules of work. And to get the number of moles, here we have to use internal energy of monoatomic gas, which is 3/2 nRT. That means for change in internal energy of it will be 3/2 nR and delta T, and which is equal to work done on the system as well. So our question is the number of moles. So let's rearrange it. So we're gonna get N is equal to 2 work on the system over 3 R delta T. So it's equal to 2 times 83.1 over 3 times 8.31 times 10. So if you calculate, you should get 0.67 moles. Question 41. So it says this problem summarizes the last 6 chapters. 0.5 moles of monoatomic gas and undergoes the cyclic process shown in a figure. Find the heat transferred to or from the gas along the process AB, BC, CA. And we have to find the efficiency of the cycle. So here it would be better for us if we define the internal energies at each state. So the formula for it is internal energy for monoatomic gas is equal to 3/2 nRT. But in this graph, temperature is not given, but by using ideal gas equation, which is PV is equal to nRT, I'm gonna replace nRT with PV, nRT here with PV. So the equation internal energy will be equal to 3/2 PV. Yes. So for each point, now we know the pressure, we know the volume, yeah? And let's define their internal energies. Internal energy at point A will be equal to 3/2 times the pressure is 5 times 10 to the power of 5 times the volume is 6 times 10 to the power of -3 meters cubed. So it will be equal to, let me calculate it, 4,500 joules. And the same, let me write it here, internal energy (4,500), and for the state B, UB will be equal to 3/2 times pressure is 3.3 times 10 to the power of 5 times 8 times 10 to the power of -3, which is equal to 3.3 times, just a second, 3.3 times 3 times 8/2. It's equal to 3,960 joules of internal energy. So internal energy for point C will be equal to 3/2 times the pressure is 6 times, I'm sorry, not 6, 3.3 times 10 to the power of 5 times 6 times 10 to the power of -3. It's equal to 3.3. It's equal to 3.3 times 3 times 6/2. Yes, it's equal to 2,970 joules of energy. So here at point B it is joules, and here it is 70 joules of internal energy. And the next step, our question is to define the heat transfer. So that means we're going to use the first law of thermodynamics, which is Q is equal to delta U plus work done by the system. So let's use it. Instead of work done by the system, I can put area. Okay, so if it is expanding, it will be work done. If it is compressed, that means it will be work done on the system. So let's solve it. Here we can, instead of converting kilopascals and liters into pascals and meters cubed, we will just neglect them, because when we multiply them, they just get rid together. That's why I will just multiply the numbers given. That means our heat will be equal to delta U is the difference of final and initial internal energies, UB minus UA, and plus the area under the line here we have, and let's count it. It will be I divided it into two parts, like rectangle, this rectangle and this triangle. So area of the rectangle is 8 minus 6 times 330 plus 500 minus 330 times 8 minus 6/2. So it will be equal to Q will be equal to 3960 minus 4500 plus 660 plus, let me count it. It will be plus 170. So first Q will be equal to will be equal to 290 joules. And let's continue. Next one. This is Q given to the system between A and B. And let's solve it for B and C. Q between B and C. If you look at the graph, B and C is the isobaric process, means pressure stays constant. That's why we will do it in this way. Again, we apply the first law of thermodynamics, which is Q is equal to delta U plus work done by the system. But here, instead of work, I will put the area again, and it will be just easier. So Q is equal to delta U plus the area. Area is this small area here. So Q between B and C is gonna be the difference. The final is 2,970 joules minus the initial is 3,960 joules of energy. So this is the delta U, and plus here it should be negative because the the gas is compressed. That's why we put negative sign here. So it will be with negative sign, and 8 minus 6 times 330. Let me count it. Minus it's equal to negative 1,650 joules of heat loss at this point. So, and the last one is Q between C and A. So this is the vertical line. That means volume stays constant. That means there is no work done. That means Q between CA is just equal to the change in internal energy. So which is equal to 4,500 joules minus 2,970 joules. And let me count it. Which is equal to positive 1,530 joules. So those are the answers. And now question B, find the efficiency of the cycle. So we know that efficiency is actually equal to work net. In a cyclic process, it will be work net, useful work net, over the Q given to the system, which entered the system. So work net in this problem can be found by looking at the area of the cycle, like interior area of the triangle. So it's equal to 500 minus 330 multiplied by 8 minus 6 over 2. over 2. And over here, heat given to the system means we have 290 joules of energy given to the system and 1530 joules, but this one second negative, we don't take it because it is negative, like that energy was taken out, spread out of the system, that's why. And we just sum them, 290 joules plus 1530 joules. So let's calculate it. It's equal to 170 joules over 20 plus 1.5. It's equal to, so sorry, we will get something here. I just got the final answer, which is 0.093 or 9.3%.